Hi, I'm Rahul, and today I'm going to talk about SIRNN, a math library for secure RNN inference. This paper was published at IEEE Symposium on Security and Privacy this year. This is joint work with Deveshwar and Mayank, who are graduate students at UC Berkeley, Kranti, who is a student at ETH Zurich, and my colleagues at Microsoft Research India, Nishant, Divya, and Asim. This work is about secure inference, and here is an example. Suppose there is a hospital who has a proprietary machine learning model which it wants to monetize, and we have Bob who has his own sensitive medical data which Bob doesn't want to expose to anyone. Now in secure inference, Bob can learn the output of hospital's model without revealing anything about his data to the hospital. And this is enabled by the cryptographic technique of secure two-party computation. Since the last couple of years, we have been working towards the goal of a push button solution to run secure inference of arbitrary ML models. Our implementations are open source and publicly available on GitHub. SIRNN is the latest among a series of work, and since the talk of SIRNN is already available on YouTube, in this talk I'm going to spend half time on SIRNN and half time talking about how SIRNN and the other papers together work towards achieving our goal. So first, let me give you a brief overview of the overall system which we have built. So everyone uses PyTorch for training machine learning models. And then we want to automatically translate PyTorch models to 2PC and 3PC protocols. To that end, first we compile PyTorch to C dot, which is a domain specific language. And this is important because PyTorch has many implicit operations. So when we do this conversions, all the implicit operations become explicit. Once we have a C dot code, we use float to fixed conversions to convert floating point models to models with 40-bit integers or 60-bit integers. This is done because secure two-party computation works much better over integers than over floating point. And once we have our integer model, which behaves similar to the floating point model, we can link it with the efficient implementations of cryptographic protocols. So having a push button system like this is actually very powerful and lets us do real evaluations. For example, we have evaluated a state-of-the-art machine learning model for computer vision in medical imaging developed by Stanford University on real patient chest X-ray images from India. And if you're interested in this study, then please visit our poster on multi-institution AI validation. The design of this tool is motivated by what we have seen in industry, and I'm going to talk to you about three main important design decisions. First is that secure inference should have the same accuracy as insecure inference. ML engineers work really hard to get every ounce of accuracy, and squandering that away is a non-starter. Second, we cannot hope to retrain a more 2PC friendly model. Basically, usually the model training teams are disjoint from model deployment teams, and getting access to training data to retrain 2PC friendly models is again a non-starter. Third, the uh, tool we have built is designed to minimize total runtime per inference, right? So what happens is that Alice and Bob want to run a 2PC based secure inference. So Alice spins a VM, Bob spins a VM, then 2PC happens, and then the VMs get shut down. And they pay for every second the VMs are on. So there is no differentiation between offline time and online time. So in particular, we cannot blow up offline time to reduce online time because Alice and Bob will be charged according to the total time. All right, so these constraints make our life hard, and which is a good thing because in research we want to solve hard problems. So when we look at secure inference, then most papers on secure inference do some kind of image classification. So we say, let's do something harder. So the problem we picked was this problem of head detection. So here we have an image and we want the machine learning model to mark all the heads in the image. And the state of the art models for this task use a combination of CNNs and RNNs. All right, so how to do secure head detection, right? So what exists, right? Secure ML showed how to do DNNs with fully connected layers On the MNIST dataset, which has 28 by 28 monochrome images, Minion showed how to do math functions and scaled up secure inference to the CIFAR-10 dataset with 32 cross 32 colored images. And then Guzzle and Delphi showed how we can efficiently evaluate convolutions using homomorphic encryption. And they did CIFAR-10 and CIFAR-100 datasets. And I have clubbed both Guzzle and Delphi together because they have similar total time, and total time is what I care about. Then came Cryptflow 2, which scaled up machine learning secure inference by an order of magnitude. So now it was possible to evaluate standard DNNs like ResNet 50 and DenseNet 121 on the famous ImageNet 1000 dataset. Now, if we consider these DNNs, then they have linear layers and nonlinear layers, right? And in all prior work, the layers were being evaluated with garbled circuits, which was a performance bottleneck. What Cryptflow 2 did was it proposed new protocols for evaluating these nonlinear layers, and these protocols drastically reduce the time taken by nonlinear layers. So much so that if you look at ImageNet scale inference, then time taken by nonlinear layers is about the same as the time taken by linear layers. So the statement that in secure inference, nonlinear layers are the bottleneck is now history. So what happens when we take these existing ML inference techniques and try to apply them to the problem of secure head detection? So the first challenge is that the head detection model is in floating point arithmetic and secure floating point is inefficient. So we use state-of-the-art techniques to convert these floating point models to integer models. Now, if you have to run these integer or fixed point models securely, then we have two challenges. First, these models use math functions like exponentiation, sigmoid, tanh, reciprocal square root, and most prior work on secure inference doesn't support these math functions. The related challenge comes from mixed bit widths. Now, when we look at the fixed point ML model, then it has low bit widths almost everywhere. But when it comes to math functions, evaluating them precisely requires high bit widths. Now, prior work on secure inference all use uniform bit widths everywhere, which means if you have a large fixed point code which contains one math function which requires high bit widths, then the whole code now needs to be in high bit width. And this is a disaster performance wise because the performance of secure inference critically depends on bit widths. So what have we done? We have created SIRNN, a library for semi-honest secure inference, and it has support for mixed bit width arithmetic, which means that you can keep on doing computations in low bit width. When needed, you can go to high bit widths, do computations in high bit widths, and then come back to low bit widths and continue. This allows us to have efficient support for math functions, and we can have precise and efficient implementations for these. Since our math functions are precise, we don't get any accuracy losses, and our performance is great, which enables us to run things like first evaluation of RNNs on speech data, and as I promised, head detection. So if we want to run our head detection model, then what all do we need, right? So the head detection model has some ReLUs, some max pools. So for there, we can use the protocols given in Cryptflow 2. And then we have linear layers and math functions. And both of these can be evaluated using our new building blocks for mixed bit width arithmetic. So what are these new building blocks? First, we have zero extension, in which we take a number and prepend zeros to it so that the underlying value of the number doesn't change, but the bit width changes. So here as an example, we have a 4-bit number and we prepend zeros to it to get an 8-bit number. And both have the same underlying value 11. In truncations, we can do a right shift to lose the least significant bits. So here we are right shifting by 4 so that we lose the lower 4 bits and we fill the empty slots created by this right shift operation with zeros. We have the related operation of truncate reduce in which we don't fill the zeros. So here we can go from an 8-bit number to a 4-bit number while getting rid of the lower 4 bits. Then we have multiplication, in which we can multiply an n1 bit number with an n2 bit number to store the result in an n3 bit number. So let me give you an example of how this will be used, right? Suppose you are doing a dot product of two vectors in which all the numbers are 8 bits. Now for the multiplication, you multiply two 8-bit numbers into a 16-bit number so that there are no overflows. And then when you sum up all these 16-bit numbers, you might want to sum up them into a 32-bit number so that again your accumulator doesn't overflow. And once you have a 32-bit answer, maybe you want to return only an 8-bit result. So then you'll do a truncate reduce to go from the 32-bit result to an 8-bit result. Finally, we have the related operation of digit decomposition, in which you can read the number as a bit string and break it down into smaller substrings. So here we have an 8-bit number and we have broken it down into 4 strings of length 2 each. SIRNN provides efficient protocols for these building blocks, which have huge communication improvements compared to the baselines. So armed with these building blocks, we can now attack the problem of secure head detection. Here we take the state-of-the-art model, which combines both CNNs and RNNs and was a NeurIPS 20 Spotlight paper. The fixed point code for this model mixes 8-bit, 16-bit, 32-bit, and 64 bits. And matrix multiplications in particular use 8-bit, 16 bits, and 32 bits. But for precise math functions, we need 64 bits. Now, if we were to use uniform bit widths everywhere, then we'll get about 3x slowdown. And with SIRNN, we are able to solve this problem in about 7 minutes of runtime. And of this 7 minutes, half the time is spent in evaluating the math functions of sigmoid and tanh. To conclude, our goal is to develop a push button solution to run secure inference of arbitrary ML models. And I want to emphasize that we are not there yet. In our toolchain, the most brittle part, or our Achilles heel, is this float to fixed conversion routine. We are given a floating point model and we want to convert it into an integer model. And we want to do that without any accuracy loss. And it's not the case that we can get an integer model and fine tune on training data set, because well, training data set is also not available. And there is some progress on this problem. TensorFlow Lite has a post-training quantization phase, which can generate a fixed point code for you. But what this head detection study showed us is that all of these float to fixed conversion routines are very brittle, and more works need to be done if you want to support arbitrary ML models. Second, we are limited to security against semi-honest adversaries, and in an ideal world, we will want both integrity and confidentiality, that is security against malicious adversaries. So semi-honest adversary is fine when we are dealing with trustworthy entities, but if we want to run secure inference with arbitrary entities, then we need malicious security. And there's some recent work which is very interesting, which is making progress towards this problem. Finally, we talk a lot about compute, but we don't talk so much about memory. Machine learning models are also memory hungry. So if we are doing secure inference and we are having a 4x, 5x memory blow up, then it is plausible that for large models, we are going to run out of RAM. So this is another problem which we need to tackle if we want to run secure inference of arbitrary ML models. And finally, some shameless advertising. We are hiring at all levels. So if you are interested in PPML and MPC, please contact us at easypeasy@microsoft.com. We have many problems with us and our small team cannot solve them all. We are working on privacy preserving ads. If you have seen the Macaw proposal, there we describe how we can use 2PC to have a more private browser experience. Then we are also working on secure validation in healthcare, where a hospital can try many ML vendors before settling in on the ML vendor which they want to go with without using any legal agreements, right? And we are hiring interns, postdoc, engineers, researchers. So looking forward for your applications. Thank you.